In this video, I want to begin to address some additional types of problems that we will cover in the differential part of calculus. And the first one is we want to be able to determine the point at which the graph of a function has a horizontal tangent line. Well, if this is the graph of my function, I want to find out the point of tangency where the tangent line is horizontal. And we know that that's going to occur when the derivative is 0, because at that point the slope of the tangent line is 0. Now that's going to be meaningful to us because that's going to be where we have this peak point, or where we have the low point, the valley point there. So all we're going to do is find the first derivative, set it equal to 0, and solve for the x values that give us a horizontal tangent, or that give us a 0 derivative. In the first example, number 2073, f of x is equal to 2x minus 1 over x squared. That's just a simple quotient, and so we're going to use the quotient rule. There might be other ways of doing it as well. For example, I could multiply, or rather first rewrite the denominator x squared as x to the negative second times the quantity 2x minus 1, and then multiply that out. And when I do that, I'll have x times 2x, or x to the negative second times 2x. I'm going to add my exponents, and so that will give me 2x to the negative 2 plus 1, or 2x to the negative 1. And then finally, I'll have x to the negative second times negative 1, so that'll be negative x to the negative second. And that's a lot. Well, all we're doing so far is working with the function. We haven't done any calculus yet, but this is going to be a lot simpler to differentiate because it's just the power rule applied to a sum or difference. So in this case, f prime of negative x will be f prime of x will be negative 2x to the negative second, and then plus, we bring down the negative 2 and multiply it by negative x, plus 2x to the negative third. Now if we want to set this equal to 0, then what we need to do is to factor out the greatest common factor. And the greatest common factor will always be, especially when we're working with negative exponents, will always be the largest negative number, or the smallest number exponent of x that they have in common. So in this case it will be x to the negative third. And since they also share the factor of 2, I'm going to bring out the 2x to the negative second. Actually, I should bring out a negative 2x to the negative second. To the negative third there. And that will leave me negative 2x to the negative third times what gives me negative 2x to the negative second? Just x. When I multiply the two common bases there, I'll add the exponents, and negative 2 plus negative 3, plus 1 gives me the negative 2. And then 2x to the negative third will just be minus 1. So when I factor this way, it really gives me a good idea of where the zeros are. Now I know that x to the negative third can be rewritten as negative 2 over x cubed, and negative 2 over x cubed won't have any zeros. It will be undefined when x is equal to 0, but there's no place where it equals 0. But the factor x minus 1 is going to equal 0 when x equals 1. And so we know for sure that when x is equal to 1, this function 2x minus 1 over x squared will have a horizontal tangent. Now with problem 74, we can't do the same thing there, because if we rewrote the denominator, we would have to write it as x squared plus 1 quantity to the negative first power, and then times x squared, and we can't simply multiply the x squared times the x squared plus 1 to the negative first. So we're going to have to use the quotient rule with this, and I'm going to begin that in the next video.